Here I'm going to talk about antiderivatives. I'm going to focus on the mechanics mostly, but I'll mention toward the end a little bit about the connections to just how important this is and why we'd be taking antiderivatives a lot after this point. So one way to think about it is simply, it's a natural thing from just a sort of puzzle point of view. Once you've learned about derivatives, we can play the mystery derivative game, kind of the Jeopardy version of derivatives. Instead of giving a function and then asking you what the derivative is, I say, here's a mystery function, and I'm going to give you its derivative, and then you figure out where that must have come from. So, for example, let's just say I'm thinking of a mystery function whose derivative is 3x squared, and we'd like to know where that came from. And for this one, it shouldn't be too hard to think about that. This is a power function, basically. And you might want to pause it, but it's most people get that pretty quickly, that since the derivative of power brings the exponent down by 1, to undo that, we would try something like x cubed. Oh, and immediately we see that that actually does work. But the derivative of x cubed is 3x squared. So we've done a simple case of this mystery derivative game. So we would say that x cubed is the antiderivative of 3x squared. But unfortunately, that's not the function I was thinking of. So if you guessed that, unfortunately, that was not the one I was thinking of. So you might think, how could that be wrong? Clearly, the derivative of x cubed is 3x squared. But the point is that there might be more than one answer here. I could be thinking of different things. And in fact, I was thinking of x cubed plus 7. Because remember what happens when you take a derivative of an additive constant, that goes away. Or I could have been thinking of x cubed plus 19 or x cubed plus any constant. And so in fact, to answer this more completely, we really would say something like, okay, x cubed plus any constant is going to be an answer. So I lied a little bit when I said the word the here. There isn't a unique antiderivative ever. So x cubed is an antiderivative, but in fact any function of the form x cubed plus a constant. So that c is a stand-in for an arbitrary constant that you could put in. Doesn't matter what it is. Could be 0, but anything of this form it works as an antiderivative of 3x squared. So this is a little bit disturbing once you think about this. That now we might have lots of other functions. You might think that there might be, okay, x cubed plus c certainly works, x cubed plus 19, whatever. Maybe there's some funky function out there that doesn't look anything like this, that when you take the derivatives, there's all kinds of cool cancellations, and out comes 3x squared. We've seen usually that when you take the derivative of a function, you get a more complicated answer, but not always, and sometimes it's surprisingly simple. There have been a few places where that's happened. And it might be possible, you might think, that there'd be many weird answers and very, very hard to guess answers to this mystery derivative game, besides x cubed and all of these x cubed plus c. But here's the really, really big theorem, and that is that you only ever have to do a plus c. Okay, so in fact, and we're going to want to actually understand somewhat deeply why this is true. In this case, only x cubed plus some constant works. So there is some ambiguity, there isn't a unique answer, but we have a precise control over all the possible answers. Okay, so these are all the possible antiderivatives to 3x squared. And so we're going to need to really justify that and see why we would believe that. So let's keep going with some more examples. Let me just change the notation a little bit. I didn't want to throw the new notation in right at the start. But there's a very common notation. It's not universally used, but there's a very common notation that the mystery function is going to be big F in this situation, and its derivative, big F prime, which will be called little f. So I'm redefining what little f means, and I'm bringing in this big F. Because we're starting with this function little f, and we don't, sometimes it's nice to just say, hey, it's its own function. We don't have to think of it as a derivative. Oh, but wait, in this context, we are thinking of it as a derivative of something, and we better give that a new name. So let's see. What if we had this being e to the x plus cosine x? Can we figure out big F, in other words, the antiderivative of little f? Okay, this one's not designed to be particularly hard, although there is a tricky bit. So the derivative of e to the x, that's the best thing you can ever be asked to either differentiate or anti-differentiate, because since its derivative is itself, we just put that here. The derivative of e to the x is e to the x. We're good. Now trig functions, sine and cosine in particular, are really nice because they just basically swap with each other but with some signs. But we have to be a little careful. Remember, the derivative of cosine is negative sine. But that's not what we're asking for. We're asking for some function whose derivative is cosine. Well, that is plus sine. So this is a very common place for mistakes, even if you're really on the ball and understand the concepts. When you're differentiating and anti-differentiating, and sometimes you'd be switching in the same problem between the two, you got to just be really careful. Okay, I'm anti-differentiating cosine, it's going to be sine. Now, once again, this is an antiderivative. To get a bunch more, you need to add any possible constant. If you add 17 or minus 23 or plus pi squared plus 4, that's still going to be something whose derivative is exactly this. And the big theorem says that you can't ever have anything that isn't equal to this function that is an antiderivative of this guy. So I'm gonna come back to the whole plus c issue in this very example in a sec. But let me do a little more complicated. So far I've been trying to make it really gentle, just get the idea. What if you had say that was, I guess that was example 2. Let's say example 3. What if you had to modify that excuse me, f of x, so that's derivative of big F. That's, let's say it was, let's modify it and says it was e to the 2x plus, and let's just to switch it up a little bit, let's say sine of 3x. And I want to get, what is my mystery? Big F, the antiderivative. Okay, so some people would guess, sometimes they'd think about, like, what if you had like a 3 times cosine, or minus 3 times cosine, or something like that. Well, is that going to work? But let's think about that. If the 3 is on the outside, it's not going to go away. A multiplicative constant will stay. Derivative of 3 cosine is minus 3 sine x. But that's going to have the 3 be on the outside. It's never going to migrate inside. So we really have to have something. A better guess would be something like cosine of 3x. Okay, now there's 2 problems with that. Well, the good thing is that when you use the chain rule, the derivative of the cosine of this inner function, it will be the derivative of the outer, evaluated at the inner unchanged, and that will mean you'll have a 3x on the inside. That's great. Now, the minor thing is the derivative of cosine would be minus sine. So here, since we're anti-differentiating sine, it becomes minus cosine. Okay. But, let me actually leave space. But there's one other thing. Let's actually just go ahead and take the derivative of this carefully. Derivative of this, can we read that yet? Of, whoops, derivative of minus cosine of 3x. Okay, minus cosine that goes to sine, evaluated at the inner function unchanged, but then times the derivative of the inner, which is 3. Okay, so that's not great because we didn't want that 3 coming out. It's not showing here. But it's easy to fix because it's a constant. And I warn you, when we get to stuff where it's a function inside of a function and we're dealing with sort of undoing the chain rule where it's not constant multiple of x on the inside, it's going to be more intricate, and it can be, it's a big deal. We have to do it, but it can be, we have to spend a lot of time on it. But because that's a constant, we can fix that pretty easily. We're just going to take minus 1/3 of that. Okay, so if that was minus 1/3, that's going to cancel that out, and we'll be on the nose. So this illustrates that we have to deal with the chain rule. We're often going to have to undo the chain rule when we do antiderivatives. In some cases, that's relatively simple, but not always. And sometimes it's really just, you get stuck. Similarly here, e to the 2x. If I did e to the 2x itself, just guessing, hey, exponentials are always simple, that would be close. Derivative of e to the 2x is e to the 2x, times 2, but we can fix that by putting a 1/2. But Don't think you can just always fix things after the fact if they're not constants. That can be a big mistake. Okay, so don't overinterpret what this example. And then, of course, plus c. And so that's getting a little more complicated. It's not super hard compared to stuff we'll be able to do soon, but it gives you an idea, a little bit of the feel for antiderivatives. In the next one, I'm going to come back to this one, talk a little bit about that plus c, and then soup this up and finish with talking about why one of the many examples why you do this.